Hello, my name is Bo. Today I will introduce RoboPack, learning tactile-informed dynamics models for dense packing. This is a joint work with Steven, Haochen, Yixuan, Cheston, Yunzhu, and Jiajun. Imagine we want to put this item into a densely packed box. How would we do it? We would first look at the scene, then attempt to insert it at different locations, finally placing it into the tray when we predict we can make enough space for it. This ability to integrate visual tactile sensing and make future prediction is crucial for many daily tasks. For example, when we peel an orange, we can sense how thick the peel is to determine how much force to apply. To enable robots with a high-resolution tactile perception, we work with a soft bubble gripper sensor that provides readings of the surface force distribution. To integrate this tactile sensing with visual signals, we propose RoboPack, a framework that integrates tactile-informed state estimation, dynamics prediction, and planning for manipulating objects with unknown physical properties. Next, let me begin with how we perform state estimation with visual and tactile sensing. At the initial time step t equals to 0, we obtain particles for each object in the scene via point cloud segmentation and downsampling. These particles represent the geometry of these objects. To further characterize their dynamics properties, such as deformability and friction, we append our object-level latent physics vector to each particle, which are initialized as zeros at this point. We define these particles with physics embeddings as our state representation. Apart from visual sensing, we also obtain tactile feedbacks from the soft bubble sensors. Using this state representation and tactile reading as input, along with the action taken in the past, we can estimate the state at t equals to 1, in which the particles and latent physics vectors will be updated based on the tactile feedback. After this, in the more general case of t equals to k, the state estimator simply takes as input the previous estimated state, tactile reading and action, and predicts the current state. This way, it can be observed that the visual observation is not actually needed after the initial step, as high-frequency tactile feedbacks enables autoregressive prediction of particle positions, which complements visual sensing that is sensitive to visual occlusion. Second, the estimated latent physics vector effectively acts as a memory module that can provide meaningful information for accurate forward dynamics prediction, which we'll examine later. After estimating the state, we can then use another learned dynamics predictor to perform future rollout. This module is integrated with MPC to find the best trajectory for a given objective. This dynamics prediction module is trained end-to-end with the state estimator on real-world random interaction data. We demonstrate our approach on two challenging tasks involving complex dynamics and partially observable physical states. In the first task, the robot must push visually similar boxes with different mass distributions to a target pose using a loosely held tool. This is highly challenging because the objects have varied dynamics, and the tool object can rotate in hand, creating complex interactions between gripper and object. The second task is a dense packing task, where there is no visual feedback except for the initial frame due to severe visual occlusion. The challenge is to identify objects that can be squeezed to make space. We present results in dynamics prediction. We show that our integrated state estimation and dynamics prediction framework is better than vision-only variant of our method, prior work RoboCook, as well as physics-based simulation methods in long-horizon prediction tasks. Second, we analyze the latent physics vectors generated by the state estimator at every time step in the box pushing task. We realized that these embeddings naturally cluster based on box types as history information accumulates. We can even train a linear classifier to predict a box type, given the latent vector. This shows that our model naturally discovers physics-related information through dynamics training, despite no explicit supervision on the physics vectors. Finally, we show that our method enables adaptive robotic control on the challenging dense packing task. Initially, the planner tries to insert the object into the near row containing two boxes. The bottom right window shows the top-down view of the future rollout planned with MPC. However, it encounters significant resistance. After receiving tactile feedback, the robot decided to switch its plan to make an attempt on the other side of the tray. And again, receiving tactile feedback, the planner thinks that the wall can be deformed, which can allow it to safely create some space for the new object. And this leads to a successful execution. The robot successfully packs the item into the tray using only a single frame of visual observation taken at the beginning of the execution. We demonstrate our method on various configurations, including ones unseen during training time. Our method is able to generalize to objects with different shapes, deformability, masses, and spatial rearrangements. The method can also be easily extended to other tasks that involve complex dynamics and partially observable states. For more details and analysis, welcome to talk to us at the poster session. Thank you.